Alright, ladies and gentlemen, welcome to the final section of this unit. We are going to be dealing with triangles, but we're going to be dealing with triangles that are inside circles. And before we go anywhere, a little bit of terminology. We've seen the words sector and arc length already, but now we have a segment. A segment is defined by a chord cutting across a circle, and the segment is the shaded part here. So a chord is any segment that goes from edge to edge of a circle that does not pass through the center. So we have this chord slicing the circle, not going through the center. This outside part that would fall off if this were a pizza, that is our segment. Example 1. So we have a sector, radius of 7, angle 0.8 radians. Find the perimeter of the shaded region. Okay, well, envision this. That is a sector minus a triangle. Yes, I hope you see that. So if we can find the area of the sector and subtract off the area of the triangle, we have our shaded area. So how do we find the area of the sector? Remember, it's 1/2 r squared theta. So 1/2 times 7 squared times 0.8. How do we find the area of a triangle? Now this is a non-right triangle, and it so happens that we know two sides, angle in between them. We have a formula for this, don't we, ladies and gentlemen? It's 1/2 7 times 7, so 7 squared, 1/2 AB sine of the angle, so sine of 0.8. Now, look at some similarities here, guys. This is pretty darn nice. Both of these things have 1/2 times 7 squared. Factor that out for a second, and we get 0.8 minus sine of 0.8. And we can put this in the calculator. We can get an area to 3 significant figures. But what I want to do here is I want to summarize this. The area of a segment. What do we see in this thing that we just found in blue? Well, it's going to be 1/2 r squared times theta minus sine theta. Now, is this something that's in the formula packet? No. Is it worth memorizing? Probably not. But it's useful to notice that we can do this, and what I would say is this idea here, that's something we all should be able to do. So with that in mind, let's jump to the second example. So we have two identical circles. Each one has a radius of 12, and each circle has the center of the other one on the circle. So C1 is the center of this circle, and it's on that circle. And the two circles intersect, of course, at P and Q. What's the area of the shaded part, and what is the exact size of PC1Q, meaning the arc size in radians? So, well, what do we do here? Let me blow this up for you. Make it a little bigger so we can work with it a little bit easier. All we know is the radius. So we know that, and we know that is 12, don't we? We also know that that's 12. And I suppose we know that that and that is 12 also. But do we need that? I don't know. Let's go a little bit further here. So, what do we know here? What do we see? We need this arc length, PCQ. We need this arc. So what we need is this angle in here. What we need is, how big is that central angle between PC1 and QC1. And what I hope that you see is that, guys, we have two equilateral triangles here. And what do we know about equilaterals? Well, we know that they're equiangular too. So, what does that mean? Well, that means that each angle in these triangles is 60 degrees, or pi over 3. So, PC1Q is equal to 2 pi over 3 in radians. So, and that, again, that's coming from the fact that PC1C2 and QC1C2 are both equilateral triangles. They both have three sides that are 12, and because of that, the three angles inside are all congruent. They're all 60-degree angles. So this angle here, 60 degrees. That angle there is 60 degrees, and we know 60 is pi over 3 radians, plus pi over 3 radians is 2 pi over 3. Okay, cool. So that's part A. But now we got to find the area of this crazy shaded region. How in the world are we supposed to do that? Well, let's have a look-see. Notice that this shaded region is made up of two of these things that I'm coloring in green. That green segment, if I could find that, the shaded region would just be twice as big. So, look at what we have. Allow me to redraw this. Looks like a lot like example number 1. So, how do we find this shaded region, this sector, or this segment area? Well, remember, it's a sector minus a triangle. If you remember that formula that I showed you a second ago, cool, but you know what? You don't got to remember it. The sector area is going to be 1/2 r squared theta, so 1/2 times 12 squared times 2 pi over 3, minus the triangle area, 1/2, 12 times 12, a times b, so 12 squared, sine 2 pi over 3. And here we go. We are ready to rock and roll, ladies and gentlemen. So 1/2 12 squared, I'm going to go ahead and factor that out again. So 1/2 times 144 times 2 pi over 3 minus sine of 2 pi over 3. Okay, so unit circle says the sine of 2 pi over 3 is, I hope you're thinking square root of 3 over 2. And if we simplify this, we will get an approximate area for this one shaded region. So we simplify this answer, and we find that the area of that segment is exactly 48 pi minus 36 square root of 3. But guess what, guys? We don't really care what the area of that segment is. What we really care about is this blue shaded area that we had up here, which was two of these guys. So what is our area going to be? Our shaded area is going to be exactly 96 pi minus 72 square root of 3. 3 sig figs would be easy enough. You just plunk that in your calculator. So, there we have it. There's our notes. 2 great examples. And a formula that, you know what, I really don't think you need to bother memorizing. But if you like memorizing stuff, go ahead and give it a go. That's all for tonight. Hope you had fun. See you tomorrow.